All right, welcome to page 2 of the notes. And so we're starting off with another application with our above formula. And this way we're able to find theta. And the reason why one of the dot product is very important is because we're able to do the dot product now, we're able to find the angle in between any two vectors that we have. That's one of the powerful things about the dot product is now that we're able to find the angle between any two vectors. And the formula to do that is right here in front of us. Cosine theta is equal to the dot product of vectors A and B divided by the product of the magnitudes of A and B. All right, so we're going to use this formula, and the first way we're going to use this formula is to find the dot product, but being able to find the dot product without actually knowing what vector A and vector B, the components of vector A and vector B are. We know their magnitudes, and we know the angle in between those, so now we're able to find the dot product. And so I'm going to go ahead and just substitute everything into our formula. So we're going to have cosine 45 degrees, because that's our theta, and we're going to set that equal to A dot B, which that's what we're looking for, the dot product between those two vectors, divided by the magnitudes, which are going to be 3 and square root of 6. So again, going back to trig, unit circle, cosine of 45 is... Good job, you got it right. Square root of 2 over 2. I hope you got it right. And we're going to set that equal to the dot product of A and B divided by 3 times the square root of 6. And then we're going to multiply both sides by 3 square roots of 6. And so we're going to get on the right 3 square roots of 12 divided by 2 is equal to the dot product. We can simplify the square root of 12 to just be 4 times 3, so we can pull out the square root of 4, which is a 2. And so our final answer is going to be A dot B is equal to 3 square roots of 3. And so now we're able to now find the dot product without actually knowing the components of the vectors. All right, now, example 4, we're going to find the angle between our vectors. So now we're actually trying to find theta. And we're going to, find an exact expression and approximate to the nearest degree. So we could do this in radians if we wanted to, but in this case, it's asking for degrees, so we're going to do so in degree. So here we have two vectors. We have vector A, we have vector B. Something that, again, if it helps if you don't like seeing these in the standard basis vector form, the IJKs, you can always just say, okay, A is just the vector 4, -3, 1, and vector B is just 2, 0, -1. All right, you can just put those, you can change the way your vector looks. You don't have to have it in standard basis vector form. All right, so I'm going to find the angle in between the two vectors. So now what we're going to do is just plug in our formula. So we want cosine theta, and we're going to set that equal to the dot product of A and B. So I'm going to do the dot product above. So we're going to have 4 times 2 plus -3 times 0 plus 1 times -1 divided by our magnitude of A, which is 4 squared plus -3 squared plus 1 squared. And then that's going to be times the square root of 2 squared plus 0 squared plus -1. squared. And so 4 times 2 is 8. 8 plus 0 minus 1. So in the numerator, we're just going to have 7. And in the denominator, we're going to have the square root of 4 squared, which is 16. Then we're going to have the square of -3, which is 9 plus 1. So 16 plus 9 plus 1 is going to be 26. And then we have 2 squared is 4, 0 squared is 0, -1 squared is 1, so it's 5. And we're going to get 7 over radical, or the square root of 5 times 26 is 130. All right. And now to actually find what theta is, we'll just do the inverse cosine to both sides. So theta is equal to the inverse cosine of 7 over 130. So that's the exact expression, and we're going to approximate. So again, you need your calculator for this. Make sure you're in degree mode. When you do that, you're going to approximate about 52 degrees. All right. Now talking about a little bit about the angle between two vectors. It says here 2 vectors A and B are orthogonal if and only if A dot B is equal to 0. So one thing that I'm going to explain is orthogonal. What orthogonal means is that the 2 vectors that we have are perpendicular. All right, and the reason why we're using orthogonal instead of saying perpendicular is because perpendicular is, the representation between 2 lines on a 2-dimensional plane that are, the angle between those is 90 degrees. Orthogonal gives us, the angle in between 2 vectors is 90 degrees, but in free space. So that's why it's called orthogonal. So the difference between orthogonal and perpendicular corresponds to 2 dimensions. Orthogonal gives us the ability to move around in free space, so in the 3-dimensional coordinate system. So that's why we say orthogonal. And you're going to find out later in Calculus 3, there's another term for, a perpendicular relationship, a 90-degree relationship between 2 vectors, which is also going to be called normal. And anytime you have 2 vectors that are orthogonal, one's going to be called the normal vector because one's going to be 90 degrees to the other. All right. And so now that we know what orthogonal means, the dot product between any 2 vectors, if it equals 0, it's going to be orthogonal. So what we want to do is we want to determine whether the vectors that are given are going to be orthogonal, parallel, or neither. So in order to tell if 2 vectors are orthogonal of each other, the dot product has to be 0. In order for them to be parallel of each other, that's something that we talked about last class. In order for 2 vectors to be parallel, they're going to be scalar multiples of each other. So we don't have to do the dot product. We can just look and see if there's scalar multiples of each other. And then if they're not scalar multiples of each other, or we get a dot product that's not 0, then it's neither. So let's go ahead and look at 24. 24, we have vector u and vector v, and when I look at these, I'm going to see, is there a relationship between these 2 vectors? And it looks like there could be. If you notice, vector u is -3, 9, and 6. The way I try to tell if 2 vectors are scalar multiples, I'll just divide one vector by the other. So I'm going to divide vector u by vector v, just the components. And I'll do 4, negative 12, and negative 8. And if they all reduce to the same fraction, they're scalar multiples. And so they look like they would. So I'm just going to show you this. Negative 3/4. It's going to reduce to negative 3/4. And the last components are going to reduce to negative 3/4. Because they can reduce all to negative 3/4, they're scalar multiples of each other. So I'll say because u is equal to, or vector u is equal to negative 3/4 vector v, the vectors are parallel. And again, you can use the parallel symbol if you'd like, just like two straight vertical lines. All right, now there's other ways too. If you don't want to do that, you could do the dot product. And if you get a dot product of 1, or you get a dot product of, or not a dot product one, I'm sorry. But there's other ways, and we'll share that in a second. But the best way to tell if two vectors are parallel is if they're scalar multiples of one another. All right, so for C, we have vector u and vector v, and we want to see if these two vectors are parallel, orthogonal, or neither. Well, they're not going to be parallel because they do not appear to be scalar multiples. Again, you could take the components of u and divide them by v and see if you get the same. You're not going to in this case. And so now, okay, let's see if they're orthogonal. So I'm just going to take the dot product of these. And so we have the dot product. And the dot product gives me a dot b. So for this one, they're dealing with vectors u and v. So vector u dot vector v, that's going to be equal to a, not vector a, but just a times negative b plus b times a plus c times 0. Negative ab plus ab plus 0 is 0, so therefore the vectors are orthogonal. All right. Now, to tell how the angle is going to appear, if we do the dot product and the dot product is positive, so that will tell us that our vector A and our vector B are going to point in the same direction. So if we do the dot product and they point in the dot product is positive, tells us they're going to point in the same direction. So the angle would be acute. If we do the dot product and we get 0, it's orthogonal. So it's perpendicular. The angle formed between those is 90 degrees or pi over 2. And if you do the dot product between the two vectors A and B and you get a negative value, it tells you that the angle between is going to be obtuse. All right. Now, to tell if two vectors are parallel and you weren't able to determine that because of, you weren't able to see that they were scalar multiples of each other, then if you realize that the dot product is equal to the magnitude of A times the magnitude of B, then what's going to happen is you have two vectors pointing in the same direction. So it's going to be parallel. All right? So that's when you have theta is equal to 0, because then that would be cosine of theta is equal to 1. All right? So again, on the unit circle, 0 is pointing in the same direction as the x-axis. And again, if you get negative 1 for your theta, so if you do the dot product of A and B and you divide by negative magnitude of A times magnitude of B, you'd get negative 1. So now you're on the opposite end of the unit circle. And so that means your theta would equal pi, which even though if they're pointing in opposite directions, so say I have two vectors, A and vectors B, Even though they're pointing in the opposite direction, they still would be considered parallel.